Of the class, we're here going to do elliptic curves, and the most important project for that is 524. I'll talk a little about 523, but most of the elliptic curve stuff is in 524. And then we have the last class. I'll talk about TLS. And that's it. After that, the final exam. Not much left of this course. So let's talk about elliptic curves, which are really important. They're the modern replacement for RSA, and until we have something better, which should be forthcoming in order to have something quantum computing resistant pretty soon, but until we have that, elliptic curves are the best things to use for public key encryption. So, let's explain what they are, and they're mighty goofy, and you have to get used to them. At first they seem pretty bizarre, and then we'll talk about how you choose a curve and so on. So, elliptic curves were introduced in 1985, of course much after RSA, which came out I think in 77. And it is much more powerful and efficient than RSA and the RSA-based Diffie-Hellman exchange. A 256-bit ECC key is stronger than an RSA 4096-bit key, and the math is, of course, much simpler and faster to use the smaller numbers, so ECC uses much less CPU to do calculations. So it was slow to adopt, though. It came out in 85, but nobody used it until 20 years later. And then it became more popular after that. It's also used in Bitcoin. Bitcoin has public key cryptography in it, using elliptic curves. And most everything based on the discrete logarithm problem can use the elliptic curve instead. Except for some reason, secure remote password, whatever that is, doesn't use elliptic curve cryptography. So, to understand what an elliptic curve is, this is the mathematical equation for an elliptic curve. And the only thing you do is choose these two values, A and B, and you get a graph like this. There's a bunch of solutions here. Notice that y appears only as y squared. So every time there's a solution in a positive y, there's going to be a corresponding solution in a negative y. The thing is symmetric about a horizontal axis. And there'll be perhaps a closed region like this, and then an open parabolic-looking region like that of possible solutions. And there'll be regions of x for which there is no y that solves it, and so you'll see no solution there. So this is just a mathematical curve on real numbers here. But what's important in elliptic curves is the discrete elliptic curves. And the way you do that is you generate a whole series of numbers, and you get a group of typically a prime number of numbers. This is prime. If 191 is prime, which it might be, this is from 0 to 190. And you generate individual XY pairs, and you can graph them here in X and Y. And as you can see, they just seem sort of randomly connected. But the point is, you have a set of coordinates that are in this elliptic curve. It has 191 dots. And you're going to just use those dots as a group, which we'll talk about here. So it's not even incredibly useful to think of it in terms of this curve, but just as sort of an abstract transformation, which we'll talk about. So first we got to describe what a field is. We talked about groups before that have an operation, and here we need two operations. We can call them addition and multiplication, although they may not be much like the normal addition and multiplication we use. But you're going to have an additive identity element, like 0, which means that when you add it to any element x, you get the same element back. So 0 is a nice way to write it down if you're thinking of normal addition. There's an inverse for addition. Minus x, if you add x to minus x, you get 0, the identity element. And you can multiply. There's an inverse for multiplication, denoted 1 over x, and we've found those inverses before. And so if you have addition and multiplication, and you have identity elements for both addition and multiplication, and you have inverses for every group member for addition and multiplication, now you have a field. And if there's a finite number of elements, you have a finite field, and those are what we're going to use for elliptic curve cryptography. So now all we have to do is define addition and multiplication. And since we're talking about these weird points that are sort of randomly scattered, it's not going to be much like normal addition and multiplication. The points are points on this curve. So if you choose a point, you have to have some rule for adding a point to another point. And here's the rule. You draw a line between them, find the point where the line intersects the curve, and invert y. So if you add p and q, these 2 points, you draw a line, you find the point of intersection and reflect it down to here. That's what P plus Q is. Now that is a strange thing to do. It doesn't seem anything like addition, but it doesn't have to be. The only point is it is some way to combine 2 elements of the group to create another element of the group. And as long as it has the right mathematical properties, that's all we care about. It is just a way to add 2 elements together. And so P is x and y, okay, xp and yp is coordinates. Here's minus p is xp and minus yp. Those are the 2 points that make a vertical line, and that goes to the point at infinity. If it was 2 elements on vertex, and the point at infinity is what you call 0. Another sort of mind-bending concept, which is why thinking of it as addition and multiplication doesn't really help much. They're just ways to combine points. So here's P plus minus P. You got a vertical line. It never crosses the curve anywhere, so you consider it as crossing at the point of infinity, and that's what 0 is. We write 0 as the point anywhere in infinite distance, up or down. A concept you might get used to if you do imaginary numbers in mathematics. They have the same concept of the point at infinity. Now, if you want to add a point to itself, you have 2 points that are the same, so you use the tangent line to the curve to find this intersection and then go down there. So those are the rules that enable you to add any point to any other point, and it has an inverse, and it has an identity element, 0. So we've now defined everything we need for this operation we're calling addition. Now for multiplication, we can just use successive addition to create multiplication. So if we add p plus p plus p k times, we're going to call that k times p. So we can multiply a point by a scalar, a number, and this is going to turn out to be very burdensome. So just like in RSA, you'll make it faster by calculating P2, P4, and P8 by adding these together, so you can do this in a logarithmic amount of time instead of a linear increasing amount of time to do all that addition. So now we have a group. This is the group. We have a set of elements like x, y, and z. We have a multiplication operation with these properties. If x and y are in the group, then x times y is also in the group. We do not leave the group. As we combine elements, we can do these multiplications in any order, and we'll get the same answer. We have an identity element. So if you multiply by x, you get x. And there's an inverse element. For every x, there is a y, such that x times y takes you back to the identity element. And this is what we had in RSA. We just didn't have the addition on the same group, so we were using a group there and not a field. So in the elliptic curve group, you'll have some points, p, q, and r, and addition form a group. If p and q are in the group, p plus q is 2, p plus q, this is the same thing we did with multiplication before. The addition follows all the same properties. There's an identity element, 0, so if you add it to the point at 0, you get back to the original point. And there's an inverse, which you get by changing the y to a negative y. That's what you call minus p. And if you add p and minus p, you get the point at 0. So we've now accomplished creating a group, and we have all the rules. You have a way to add things, a way to multiply things, and it obeys the properties, so we have a finite field. So now we can define the problem. And here's the problem. You always have to have a hard problem. So if I have p and q is k times p, finding k is turned out to be very difficult. This is like the discrete logarithm problem. Since adding p again and again does crazy random things, it doesn't just add like normal numbers, then it's very hard to find out how many times you'd have to add p to itself to get q. And that is the hard problem. So your public key will be q, your private key will be p, and nobody can figure out how to determine one from the other. That's what's going on here. So if that problem is hard, we can now do it. Now, so if you have a ZP, where P is n bits long, the security is n over 2 bits. So if you use a 256-bit long P, then you get 128 bits of security, which, as we said, is enough to be uncrackable by any any computers that we have now. And that would be more than 4096-bit RSA, so much faster, much shorter numbers to work with. So now you can make the Diffie-Hellman key agreement, now that you have a hard problem. So, first person makes up a secret A, this person makes up a secret B, then you have a starting point G, which is a generator of the group. They transmit G to the A. This is RSA. They G to the A and transmit G to the B, and then they calculate G to the AB on both ends. This is how RSA works, by using exponentiation. In elliptic curves, it's just multiplication. You choose a fixed point G, which is a generator of the group, and now you pick a random number, dA, and multiply G times dA, and that's your public key, PA, which you send over here. And this person does the same thing, secret DB, and calculate a public key, PB. And then you multiply this, your secret key, times the other person's public key, and you get this quantity, DA, DBG, and the person at the other end gets the same thing. So you have now agreed on a shared secret by transmitting only public keys, and because the Diffie-Hellman problem is hard, you cannot deduce DA from PA. That's the fundamental point. So the logic is just the same as RSA, but the math turns out to be much faster. You can sign with elliptic curves. Same thing, this is elliptic curve digital signature algorithm. This is what's used in Bitcoin. And so you have signature generation and verification. So to sign it, you have a private key, and verifiers have a public key. So you can use your private key to sign something, and people can verify it with your public key. All they have to know is which curve you're going to use, its order, the number of points, and the coordinates of a base point G. And they can then verify a signature. So you hash the message with something like a SHA function. Then you pick a random number and calculate K times G. And the signature is these quantities you derive from it. And the point is you can verify those at the other end with knowledge of only public things. All right. So if the coordinates are 256-bit numbers, then RNS are 256 bits long, and the signature is 512 bits long. All right. So RSA is used for encryption and signatures. ECC can do many things: encryption, signatures, key agreement, and identity-based encryption. It has more features. And RSA's signature and verification are simpler than elliptic curve. And the RSA's verification process can be faster if you have the small public key E. But ECC is faster at signing and has shorter signatures. So there's a measurement, I think, of time here. Yes, ECG, elliptic curve, is 150 times faster at signing than RSA and somewhat faster at verifying. So that's why it saves everybody a lot of CPU time. All right. You can actually encrypt your data directly with elliptic curves, but the problem is you can't encrypt any long message. You can only encrypt about 100 bits. So that's not really enough to encrypt much of anything. So you don't normally do it this way. What you normally do is you use Diffie-Hellman to have a shared secret, then you run it through a key generation algorithm, and then you use AES to encrypt with that key. That's the way you typically do it. So here's the integrated encryption scheme. Pick a random number D, calculate the public key Q from D of G, then compute a shared secret by combining D times the public key of the other person. Now use a key derivation scheme to make a key from that, as we've done before, and then encrypt things using a symmetric authenticated cipher like AES or AES with an authentication tag. Now you're ready to send messages with security. All right, so the only issue is now left is choosing a curve. Now, here's the basic way to define a curve. There's the number of points, called the modulus. There's the A and B that you have in this equation, and then there's an explanation of why you chose that A and B. These are things that you would consider when deciding how secure a curve is. So the order should not be the product of small numbers. If it is, then there will be, it should be a prime number, or at least something that's not got small products, or else you'll have little loops that just repeat a few numbers over and over, and it'll be easy to reverse the problem, the hard problem, the elliptic curve discrete logarithm problem. And it's better to have curves that treat P plus Q and P plus P the same way to avoid side channel leaks. If you have in certain conditions, you have a different calculation. That's called the unified addition law. And you should explain how you chose the A and B. If you present a strange choice of A and B and you don't say where you got them, then people will be concerned that you have somehow carefully chosen A and B maliciously to get a weak curve. And that's, of course, what the NSA did. So National Institute of Standards standardized this in 2000. They have 5 prime curves. These are the most commonly used ones. There are 10 others that are rarely used. And the most common one is P256. The modulus is P, this number, 2 to the 256 minus a few numbers. And it's this equation. There's a 3 here. And B is some long 256-bit number. And what B is you take this number and you calculate the SHA-1 hash of it. And they will not explain why they did it. And so your book, some cryptographers like the authors of your textbook believe that there's no backdoor. However, Bruce Schneier believes that there is a backdoor, and he is a very influential cryptographer. He said, I no longer trust the constants. I believe the NSA has manipulated them. I looked at the random seed value. No justification is given. I now personally consider this to be smoking evidence that the parameters are cooked. And the problem is we have caught NSA and NIST doing this several times before, deliberately lying to people, tricking them into using unsafe parameters so that the NSA can read your stuff. So in general, a lot of people don't trust these curves, like Bitcoin and Tor, and many applications refuse to use them, and instead use other curves that are not approved by the government because they suspect the government is betraying you. It has not been proven, but it certainly is possible. So if you don't want to use the official NIST approved curves, then what most people use is 25519. This is faster than NIST, it's quarter keys, and no suspicious constants, and it has this property of using the same formula for both kinds of addition. So this is the one you've got. Here's the prime number, is the prime number closest to 2 to the 255, which you could have done in the projects here. The closest to 255 is 19 below it. And this is used all over the place, but it's not approved by the government. So here's another one. This is what Bitcoin uses, 2 to the 56 minus another couple of numbers. And there's a lot of other curves. France made some, Germany made some. There are newer curves again. Various other ones, even longer ones, even more bits than 256, although most people just use 256-bit encryption because it's good enough. And so here's how things can go wrong. It's got more parameters, and so you might make mistakes in coding, and you might have side channel attacks, watching things like timing and power consumption. Signing uses a secret random key number k, like an initialization value, and if you reuse that value, then the attacker can calculate it. So you have to be careful not to reuse the secret, and this happened on the PlayStation 3. They made this mistake in 2010, and the hackers were able to find their secret key. There's also, this one's pretty nasty and specific to elliptic curves. So remember, the proper transaction here is I would pick a secret, then calculate the public key from the secret and send it to the other person. Now, if I'm a malicious attacker and I want to learn your secret, I can not create a DA, but instead transmit a malicious P. I can take a P that is not on the curve you expect it to be on. It's on a different curve, which is easy to reverse the elliptic curve discrete logarithm problem. Choose a curve that, for example, just hops around among a few values, which we'll see. When we get to the project later, I'll demonstrate this. So if your calculation here does not verify that the P I give you is in fact on the curve, when you multiply it by your secret and send it back to me, you might be exposing your secret. And that's what this trick is. So this is a sneaky, nasty trick. By pretending to be engaging in Diffie-Hellman handshakes when I'm not, I can lie to your server and get it to transmit a number to me that exposes your secret. That's pretty nasty. So the cure, of course, is you have to verify that the response you got is in fact in the group over here, before you just multiply it by something and send it back. All right, and so that's the game here. And some of the TLS implementations were vulnerable in 2015. So this is the problem. You invent all these fancy schemes, but they all have flaws. Anyway, let's take a look at a Kahoot. Should be here. I think this is chapter 12. It is chapter 12. All right. Right. Put them closer together. I should have a chapter 12 Kahoot. There I do. All right. late, you say? Yeah, sure. How about choosing a string in number pi randomly to form p? Below fixed pictures boxes in pi. Well, I don't really understand the question. There was, you really mean pi, like 3.14159? Because that's not random. Have we got any more people who want to do this? If there's only 3, it's a little silly, but I'll do it. I'll give it another few seconds. What's that? Yeah, most of them are tuning in online. Yeah. So if the NSA put a backdoor in their curves, did you know what that would look like? Something like well, Pete, nobody knows, but the most likely thing is what it would do is it would mean that you have a secret way to reverse the discrete logarithm problem. There's no obvious way to tell. That's the thing. That's why you want to know where they got the numbers A and B. Well, anyway, let's go ahead with this. That's the problem. You encrypt stuff, and you really don't know that there isn't a secret backdoor into it. All right, so how long should the ECC key be? All right, that's 256. That's right. That's the standard length everybody uses. All right. All right, how long a message can you encrypt with AES? Any length? We've been through this. You use a block by block, and you can do cipher block chaining or something. You can have as many blocks as you want. Any length is okay. All right, which curve is suspected of having the NSA backdoor? That's the one, P256, the official government-approved one.
I thought it was like Julie C or something.
What's that?
I thought it was like Julie C or something.
Julie C?
Or like dual
EC. Yeah, there is one called dual EC, which is another one that was proven to have a backdoor. And they paid RSA $1 million to make it a default. That was another one. This one is the one that has not been proven, but they suspect.
Okay.
And because they did it to dual EC and other ones, then everybody doesn't trust the NSA.
Right.
Yeah, good. All right. Answer, how long a message can you encrypt with elliptic curve? Yep. Nope, not any length. Whoa. Wait, ECIS, I think that's the complete system, yeah. EC alone can only do 100 bits, but I think the ECIS is the combined system that effectively uses AES. Yep, this is the integrated encryption scheme, which again, it agrees on a secret and then makes a symmetric key and then uses AES, so again, it can do any length. Okay, good. All right. All right, so we record the winners. All right. Stop this recording.